Hello everyone, I'm Xingmin Wang, a third-year Ph.D. candidate from the University of Michigan, advanced by Mr. Henry Liu. Today I will present, the topic I present today is the data infrastructure for connected vehicle applications. So the data infrastructure we built is based on the Arbor connected vehicle test environment, which is short for AACVTE project. And this project comes from the original safety pilot model deployment, which was started in 2012, and in 2015, the safety pilot model deployment project becomes the current AACVTE project, which is still the largest operational real-world deployment of connected vehicles. And for the vehicle deployment, the AACVTE project has totally installed over 2,500 vehicles, which were either equipped with aftermarket safety devices or the vehicle awareness devices. And from the infrastructure side, the AACVTE project has installed over 75 roadside units, including 69 production sites and 6 testing sites. And all the roadside units roadside units collects the basic safety message data and broadcast the signal phase and timing data at the same time. And the communication range between the vehicle and the roadside infrastructure is about 100 to 200 meters. And for the data contents, we have two main data sources. The first is the basic safety message data broadcast by the vehicles, which follows the SAE standards. And this message contains the real-time latitude, longitude, and time step, and also other safety-related messages of the vehicles. And the other data source is the SPaT data, which is the signal phase and timing data. And this data is sent directly from the controller, and this data set contains all the signal phase and all the signal states of the intersection phases. And for the resolution and the transmission delay, both this data was sent for every 0.1 second, and the delay were within 1 second, which can definitely support the real-time applications. And based on this data collected from the AACVTE project, we built a data infrastructure to process and visualize the raw data for the real-time connected vehicle applications. And basically, the data infrastructure contains 3 parts. The first is the data receiving parts. And the second is the data pre-processing, and the last is the upper layer applications. And for data processing, we have 2 different data sources. The first is SPaT data, and then is the BSM data. And both these data have to be decoded before it can be finally used. And from the other side, we also need offline map data, which is from the open source map, OpenStreetMap. And for the data processing, the most important part is to map the trajectory data to the road and associate with the signal phase and timing data. And with this match the trajectory data and the signal phase data, we are able to draw some aggregated time space diagram to evaluate the traffic signal control as well as the safety issues. And for the upper level applications, there are lots of potential applications that can be built based on this data infrastructure. So far, we have drawn some plots to evaluate the efficiency of the intersection signal control, and also we can also use this data to do some safety-related study. For example, to generate some safety measurements to evaluate the safety issues. And due to the limited time, I will skip some of the data pre-processing procedures, such as the denoising and the smoothing. And the most important part of the data processing is the trajectory data map matching. And for the BSM data we collected, it's only collected near the roadside units. So the map matching here is to match the trajectory data to the corresponding movements. And here we use a hidden macro model to match the trajectory data. As shown in the left figure, both the movements shown by the blue lines and the trajectories shown by the red lines can be represented as a vector composed of series GPS points. And the xi here is the GPS point of the trajectory, and the di here is the distance between the trajectory point and the road movement. And the phi here is the angle between the vehicle trajectory and between the heading of the vehicle trajectory and the road movement. And for the hidden macro model, it's we consider two factors to do the map matching. The first is the distance between first is the state probability, which is the distance between the GPS point and the road movement. Here we assume that given a trajectory it belongs to a road movement, the distance follows the Gaussian distribution. And the other side is the transition probability in the hidden macro model. Here we define as we define this as the hiding angle between the vehicle trajectory and the road movement. Basically, here we assume that the transition probability follows exponential distribution. With these two factors, we can calculate the total probability as the production of the state probability and the transition probability of all the trajectory points of a given trajectory, and then we can maximize the total probability to get the movement that this trajectory belongs to. And for this map matching problem, it can be efficiently solved using the dynamic programming algorithm. And here are the results for the trajectory data map matching. And each subplot stands for a movement of the intersection. The horizontal axis is longitude, and the vertical axis is latitude. The blue points and the dots are the road, and the red points are the matched trajectories. As we can see, using our algorithm, almost most of the trajectory points were matched to the road correctly. And combine the signal phase and the timing data and the matched trajectory data, we can draw the aggregate time space diagram to evaluate the traffic intersection signal control. Since most of the traffic signals in the city of Ann Arbor are actuated or adaptive signal control, which means that the cycle lengths of different cycles are usually different. So here is what we do to draw the aggregated time space diagram. We have the trajectories of different cycles, and we can shift the trajectory in different cycles so that they share the same green start time. And finally, we can draw the aggregated time space diagram, which will be frequently used to evaluate the efficiency of the intersections. And to evaluate the traffic signal control, we also draw the stop delay scatters and the stop position scatters to evaluate the performance of intersection signal control. So the left figure shows, given a trajectory data, how we can calculate its maximum stop position and also the total stop delay. And with this method, then we can plot each trajectory as a point to get the stop delay, stop position scatters and the stop delay scatters as shown by the two red figures. So the horizontal axis is the time of day when the vehicle traversing the intersection, and the vertical axis is the stop position and the stop delay accordingly. And based on these figures, we can easily evaluate the efficiency of the intersection signal control. And then I will give more examples. And this is we use 5 week state data from the Maiden Lane and the Fuller Street located at Ann Arbor. And this intersection have 8 phases. And here is the aggregated time space diagram of the 8 movements. For movements, we can clearly see the departure shockwave since we have all the trajectory data have the same green start time. And these figures are the stop delay scatters, and from these scatters we can clearly see the stop delay of the different movements of the intersection. For example, for the phase 5, if we draw a line, horizontal line as a cycle length, all the plots above the cycle length means that this vehicle did not pass the intersection within 1 cycle. This means that this intersection has suffers a lot from the oversaturation. We can for the optimization, we can increase the cycle length to avoid the oversaturation to reduce the total delay of the vehicles. And for the stop position scatters, basically we can roughly see the Q length of the from this figure. For example, we can see from the fifth 6, we can see a long queues over 140 meters, and this long queues would cause the very severe traffic congestion. It would cause spillover as an adjacent intersection, and also as well as the gridlock for the urban traffic network. And based on this evaluation and plots, we also develop a website which we usually call it is AACVTE live website, and in this website we can visualize all the plots and all the data. So can you see the slide? Can you see the website now?
Yes.
Okay. In this plot, as shown in this figure, all the red markers are the locations where the roadside units were installed, and all the blue points are the real-time trajectories. And this is exactly the 5 minutes from. There is only a 5 minutes lag from the real time, and all these blue dots are the real-time vehicles. And from this website, if we click on the markers, we can see the basic statistics of the, for example, of the specific intersection. For example, the number of vehicles passed by the intersection for different phases, also the average stop delay, average stop positions, and also the plots we mentioned before, including the stop delay scatters, the stop position, the time space diagram, and also the number of vehicles within the day. Okay. As we mentioned before, there are different applications that can be built based on these data infrastructures that were developed. For urban traffic mobility, we can use this data to traffic estimation and traffic signal control. Actually, this is what I have done all the time. And on the other side, we can use this data to do some safety measurement. For example, as far as I know, I'm very glad that this data set has supported at least 2 projects. The first is to use this data to identify the aggressive drivers, and the other is project I know is to use this data to detect the dilemma zone, and also to furthermore to optimize the red and all red, the yellow and all red clearance time of the intersection. And thanks for listening. Basically, that's it.
Yes, I have a question. I'm trying to understand your whole overall process. So the cars which are equipped with the receiver for the connected vehicles, they are driving around and they're communicating with the infrastructure, and then the cars are sending to a server this data. Like, where is the raw data coming from, where going to where before you're doing the processing?
Okay, I'm sorry that I did not make this part clear, and I will try to explain it. So the first, the car equipped with the onboard unit can broadcast the basic safety message, and this will send this data will be sent to the roadside unit via the DSRC, and then the DSRC transfer the data via through the IPv4 to another city network, and then the data was forwarded to the server located at the arm tree, and then we can query the data through the UDP.
So what is the delay from when the car is sending the data to when it arrives at arm tree? And then what additional delay for processing?
Here is the delay. So the average delay for the basic safety message is about 0.3 seconds, which means that from the data was generated from the onboard unit until we receive it, the overall delay was about 0.3 seconds.
I see. So overall delay is around 0.3 seconds. Okay. Thank you.
Thanks.
So now currently, when we look at traffic signal performance measures, we talk about arrival on green. So is your system equipped to measure that so that we can do some automated signal performance measures?
Yeah. Actually, currently we use these 2 plots to evaluate the traffic signal control. The first is the stop delay scatters. Basically, we calculate the stop delay for each trajectory and plot this to these scatters. And for example, for this point, it means that a vehicle passed by the intersection at around 10 a.m. and the stop delay is over 2.5 minutes. And we can use these plots to evaluate the green split of the intersection. For example, if one of the phase has much larger delay than others, which this means that we should assign more green time to this phase. And we can use these plots to to evaluate. We can definitely use this plot to evaluate the traffic signal control. And this is for the delay. And we also have the stop position scatters. This stands for the Q length of the different phase.
Now, you talked about applications for transportation engineering. How much penetration of vehicles, for example, do you need 20% connected vehicles in a traffic stream to come up to having useful data for these traffic applications?
Well, that's a very good question, and this is a research topic I have done since last year, and the intuition is that if we have different level of the penetration rate, we can do different levels of the traffic signal control. For example, if the penetration rate is too low, then maybe we can only use it for the fixed timing plan optimization. But with the higher penetration rate, we might be able to use this data to perform the real-time signal control. But for this data set, currently the penetration rate is less than 3%. So we might not be able to use this data for the real-time traffic, real-time signal optimization, but we might be able to use this data to optimize for example, a fixed timing plan or something like that. I think the penetration rates will be okay for the fixed timing plan optimization.